Hi, everyone. I'm Divya Bhargov from Postgres team at Microsoft. Today, we are going to be diving into the real world performance gains of Postgres 18 over 17 using actual production query patterns. No synthetic benchmarks here, just SQL you'd really run. Let's explore not only how much faster it is, but why it's faster and what that means for your workloads. Now that we've introduced this, let's understand the side by side performance wins in real world query patterns between Postgres 17 and 18. I set up two identical environments on Azure, same platform, region, compute size, storage, pricing tier, etc. The only difference, one ran Postgres 17 and the other Postgres 18. That way, we could isolate the performance differences purely based on the version upgrade. Here's the testing methodology I used. I ran 7 times per query per server. That took a median to keep the timing stable without the system jitter. I discarded one warm up run, so we measured cache hot performance and not the first touch latency. Timing came from explain analyze. So this was the server side execution only, no client or network noise. In some cases, I set enable sequential scan to off on both the versions. This was in order to push the planner towards index plans where it was applicable. Now let's talk about the test tables and the data that I loaded. I had mostly tables modeling realistic workloads, stock transactions, trade log, companies, watch list, etc. You probably guessed my hobby at this point. The sizes range from about 20,000 to 5 million rows each. And I had created appropriate indexes and keys for the join and filter columns. And the companies table had a self joining view so that I can explain the self join elimination test that we'll be looking at a little later. All right, let's kick off with something we all know, those queries with multiple OR conditions. Now, here's the first big improvement, the OR to any transformation. Picture the kind of queries you write every day, filtering by multiple statuses. Or maybe you have got a report that filters by list of categories. In Postgres 17, when you write where clause and with multiple OR conditions like this on the same column, each OR triggers its own index scan. It builds its own bitmap, and then the planner merges them. It's extra work, multiple bitmaps, multiple index traversals, and merged it. Now, think about some real world use cases. Maybe you've got an application that filters by region codes or multi tenant systems that filter by account IDs. The more or conditions you add, the more the overhead. Postgres 18 changes the game. Now the planner can see that OR chain and automatically rewrite with and like with a single index scan. There's no array lookup or there's no merge. And here's the best part: you don't have to change the query at all. It's done at the planner level. Now let's talk numbers. We ran a benchmark, a query with 5 OR conditions, 5 firms, like you see in the screen here. On the left is the PG17 numbers, and on the right is PG18 numbers. On PG17, we got this query running for within 34 milliseconds, and at PG18, that was only 19 milliseconds. That was like a 43% improvement, almost twice as fast. Now, a single query saving 15 milliseconds may not sound that huge, but think about an API endpoint that runs this query 1,000 times per second. You're freeing up CPU time constantly, and that's how this kind of improvement could scale without you lifting a finger in the application code. Now, let's look at what's actually happening under the hood. On the left is Postgres 17 execution plan. And on the right, you got the Postgres 18 execution plan. And this is the pattern we'll use for all my improvements that I'm stating today. And just note that I have the excerpts of the plan, which are actually important. The real plan is much larger. So, so look at the left here. You got the bitmap OR node merging 5 separate bitmap index scans. Each OR condition triggered its own index traversal, its own bitmap, and then they all got merged. Now look at the right. Postgres 18. No bitmap OR, just index only scan with any expression. One clean index traversal and no merge step. So because index only scan is used, it can get all the data that it needs from the index and without any heap access. That's the beauty of this improvement. Less work, fewer resources, faster results, and it's all automatic. Your query stays the same. The planner just got smarter. Now that was improvement number one, right? So we're going to talk about our next improvement, number two, the planner getting smarter about how it navigates your indexes. And this one gave me a huge speed up. So let's talk first a little bit about composite indexes before I get into the story. I'm sure at least some of you here would have been burned by the leftmost prefix rules. Setting the scene here, you got a trade log table, 5 million rows. You got a composite index on the exchange and trade ID. It makes sense, right? So your query by exchange and trade ID together all the time. Most times that's your pattern. But then someone writes this query: select count star from trade log, where trade ID is 900 million, like is so shown in the screen here. Notice what's missing. There's no predicate on exchange, the leading column of the index. And in Postgres 17, that's a problem. See, a B tree composite index is like a phone book, sorted by the last name first. So, and then the first name. So, if you want to like find someone named Divya, but you don't know the last name, you can't just flip to the right page, right? So you end up reading through far more parts of the book that you wanted. um, that's close to what Postgres 17 often does here. It has the index. It can see trade ID is in there, but because Exchange isn't filtered, it often ends up scanning a large portion, sometimes effectively all of the composite index. Um, and that's applying trade ID as a post filter. So on 5 million rows, that can be really painful. So let me actually jump to the next slide, which talks some numbers here. Um, so, what does the skip scan actually do? Instead of scanning the huge portion of composite index, Postgres 18 internally iterates over the distinct values of the leading column. In case exchange, and then for each one, it performs a targeted search directly to match the trade ID. Think of the phone book again. Jump to, let's say, the B section and found Bhargav. Next, look for Divya. Jump to the next last name section, look for Divya. Skip, skip, skip. Instead of walking through millions of entries, you are only making a handful of precise probes. And the numbers speak for themselves. Same query, same table, same index. And it just gets way better in Postgres 18. Like you see in this picture, 121 milliseconds for Postgres 17 and barely 0.07 milliseconds for Postgres 18. That's not like a 2x faster. It's not even 10x faster. It's like 1,741 times faster, like 99.9% reduction in execution time. Now, why is this gain so dramatic here? Because the leading column exchange has a very low cardinality. In our dataset, there are about 12 distinct exchanges: NYSE, NASDAQ, and so on. So Postgres 18 can do about 12 targeted index probes instead of scanning a portion of the 5 million row index. The fewer distinct values in the leading column, the bigger your win is. If there were 1,000 distinct values, the planner might decide skip scan isn't worth it, and it will fall back to another strategy. Let's look at the execution plan here side by side to see the difference. Um, as usual, on the left is Postgres 17. Like you see, it's doing an index only scan using the index for exchange and trade. Sounds efficient, but if you look closer, the index condition isn't using trade ID as a seek condition, it's applying as a filter. That means Postgres is walking through a large portion of the composite index, reading entry after entry, checking each one. Does the trade ID equal 900 million? Yes or no? Next. Yes or no? Next. It's using the index, but in a very expensive way. A broad scan with a post filter. That's why it took 121 milliseconds. Now let's come to the right, Postgres 18. It's still an index only scan, right? Um, but now trade ID 900 million appears as an index condition, not a filter. In Postgres 18, the scan performed multiple targeted index searches rather than walking the index as one long scan. Conceptually, um, each search corresponds to a distinct value of exchange, as if the planner was probing NYSE, like exchange equals NYSE and trade ID equals 900 million. Next, exchange equals NASDAQ and trade ID is 900 million, and so on, right? So, a handful of targeted lookups instead of millions of sequential reads. That's why it completes within 0.07 seconds. And remember, the fewer distinct values in the leading column, uh, the fewer distinct values, I mean, the bigger the win. So low cardinality leading columns like status, region, exchange, account type, these are all cases where the skip scan can really shine. And guess what? Those are exactly the kind of columns we often put early in composite indexes. So that's two wins so far. Smarter or handling, smarter index traversal. Both are automatic. Let's keep going. All right, improvement number 3. And this one's my personal favorite because it catches something you'd never think to look for. Um, let's look at this query. It's dead simple. Select star from company view where sector equals tech. Nothing exotic here, right? But here's the catch. Under the hood, company view is defined as a self join of the companies to the company's table itself on the primary key. So if you're thinking who would write a view that joins a table to itself, the answer is it happens all the time. The ORMs, Django, Hibernate, Entity Framework, they generate this kind of self join, which is redundant all the time. And as applications move towards microservices and clean architectures, you get views on top of views on top of views, the same base table, joined 3 or 4 times. I call this the abstraction tax. And until now, Postgres paid it in full every time. Now, numbers. So, Postgres 17 took 6.29 milliseconds, and Postgres 18 just 1.28 milliseconds. Again, 5 times faster about. So, what changed? So, Postgres 18 introduces a new planner optimization that can automatically remove some unnecessary uh, table self joins. So when planner detects that a table is inner joined on itself on a unique or primary key column, it uses a mechanism called inner rel is unique. To improve that, every outer row, there is exactly one inner matching row, and it's the same physical row. So once proven, it replaces the self join with semantically equivalent single scan. No extra table access here, no extra join step. There is a fun bit of story here. This optimization was actually attempted in PG17 itself. It was committed, but late in the release cycle, it was reverted before it made it to the PG17 release to allow for more refinement. And then it was again recommitted early in PG18 cycle. And it has been pretty rock solid ever since. This is controlled by a guck, a parameter that is called enable self join elimination. It's on by default, so you can get this for free just by upgrading. One important caveat to this is this optimization only takes into consideration plain tables. So if you've got self joins on CTEs or subqueries or other complex constructs, those won't be eliminated, at least not yet. Let's pop the hood and look at the actual execution plans side by side here. On the left, Postgres 17. You can see a merge join with two index scans on the company primary key labeled A and B. That's the same table. That's the same table, same index, scanned twice, then merged together without really self join elimination optimization or any such. The planner treats this as a legitimate join, and it does all the work, 6.29 milliseconds. On the right, Postgres 18, just a single sequential scan on the company's table with sector equals tech filter. The second scan, gone. The merge join, gone. The planner detected that self join, that it was a self join. Based on the primary key, it confirmed that it was unique, proved that the join was redundant, and eliminated it entirely. Half the work, much simpler plan tree, and just way faster. All right, moving on to improvement number 4. Take a look at this query. Classic aggregation pattern. You've written queries like this 100 times. We're selecting ticker, name, and sum of shares from our stock holdings, grouped by ID, ticker, and name, ordered by ticker. So maybe you're building a portfolio summary or a leaderboard of the most traded stocks. Now, here's the key detail. In this demo, ticker has a unique index. So if I'm trading AMD or if I'm trading NVIDIA, they're all like unique indexes. They may have an ID, but they all have unique ticker symbol. And the column defined as not null, right? So that matters because once you know that the ticker, you already know the corresponding ID and name. Those columns are functionally dependent on the ticker. But the query still groups by all three columns ID, ticker, and name. This is a common habit we use to include every non aggregated column in the group by. Now, here's the interesting fact. Postgres has actually been able to prune redundant group by since version 9.1, but only for primary keys. If your column just had a unique index, the planner treated it as just another index and wouldn't use it for pruning, right? So this is where uh, the group by pruning for unique indexes got introduced. So here's the difference in the plan. We got like 13 milliseconds versus zero point zero 0.05 milliseconds. And like you see, the plan here is super interesting. You got on the left, you got a group aggregate with group by key, ID, ticker, and name. And on the right, you see that it's an index only scan, and the group key is just the ticker. That's the difference here. And now we jump to our final improvement that I'm going to talk about today. Um, this one targets on set operations. Specifically, here is the set difference, right? Select a ticker from watch list, except the ticker from my portfolio. So basically, what this states is show me everything I'm watching that I don't already own. So you see this pattern everywhere, like in reconciliation, portfolio comparisons, inventory differences, anywhere you compare two lists and you want to find what's missing. The sequel itself is simple, but in older versions, the execution plan has more internal machinery than you'd expect. So Postgres 18 makes this machinery way better. And that's the improvement in the speed, about 1.5x faster. After looking at my other speed ups like 272x previously, or like 99% improvement, 1.5x may not sound as dramatic, but this one's an interesting one for a different reason. This is not a schema trick. This is not only because we created a better index, this is also because we did not rewrite the query. This is basically Postgres 18 cleaning up the execution machinery for hashed set operations. Um, I will keep uh, uh, the plans side by side at this point, and like you see, there is on the left the hash set operation uh, has basically has it accept, then append, then two subqueries can select star one, select star two, each wrapping an index only scan. So that's not our SQL's fault. It's just how the old executor represented each of these set operations internally. And on the right, you see it's just a hash set operation, except with two direct children, index only scan on watch list and index only scan on the portfolio's primary keys. So no append, no subquery scans. All the plumbing is gone. It's just a much cleaner structure, and it also enables short circuit behavior with except, right? And similarly, similar wins with respect to intersect, and all these all these set operation wins come automatically. It's again my my statement in this whole uh, setup is it's the same SQL, same setup, just upgrade, right? So let's step back and take a full picture. I spoke about 5 improvements today. Same queries, same tables, same hardware, just version upgrade. Or to any, where the planner rewrites uh, or chains into any. B3, skip scan, that's the big one. Postgres 18 can now skip through a B3 index instead of falling back to a sequential scan when the leading column isn't in your where clause. Self-join elimination, which is about 5 times faster. The planner detects basically when you're joining a table onto itself, and it removes any redundant scan entirely. Just less IO, smaller plan. Next is the group by pruning. This is when you have unique indexes or not null columns. Now, the planner can prune redundant group by keys, which cascades into your index only scans and eliminates sorts. And finally, except hash, which is about 1.5 times faster. It's structurally a cleanup of set op executor. Smaller win, but it applies to every except and every intersect that you run. So those 5 were the benchmarks I had time to demo. But in this slide, I also listed many more improvements, especially with the executor, planner, and optimizer, as well as the monitoring, which all makes really good reasons for upgrading to Postgres 18. Now, should you upgrade? I've put up a quick checklist based on today's demo on what are some reasons why you may want to upgrade. Apart from all these things that I discussed today, if you're running partition tables at scale or concurrency, OLTP, the planner and lock stability work has you covered as well. Now, should you test thoroughly before upgrading? Absolutely. That's true for every major version. But in my experience, the answer to should we upgrade is almost always a yes. And with PG18, it's a pretty enthusiastic yes. My recommendation is start with your read heavy workloads, and that's where the wins are mostly. And like I said, same SQL, same application, just upgrade. And that's your Postgres 18 story. Thank you all for the time that you gave me today. And I hope the next time you run, explain, analyze, you smile at the plan. Thank you.